Great, thank you. Nice to meet you. First of all, I'm Emanuele Bozzi, postdoc at University of Pisa, and right now, actually since the start of my PhD in 2021, I'm working with DAS-related topics. And during my postdoc, I'm developing an automatic DAS channel selector tool, which is then integrated with a locator for hybrid networks. So, which merges together fiber optic sensors with conventional sensors. So today, what I will describe is the automatic channel selector we developed, which is called ORION. So, which is basically a work under the framework of the Geo8 project, with data from Bochum University, Institut de Saint-Mar, and a collaboration with INGV. Okay. So first of all, what I wanted to do was in introducing the next generation integrated networks. So basically, which combine basically the existing surface-based conventional networks, which are often sparse, tens, hundred sensors, with the new and sensor based on fiber optic, both on the surface, for example, using telecommunication fiber optic cables, which are distributed sensor, but also affected with often complex data, given the fact that with us we have uniaxial sensitivity and the variability of the coupling with the ground, or if we are lucky, ad hoc fiber cable installed in wells. In this case, we have an higher signal quality, but often poorer azimuthal coverage, given the fact that the wells can be vertical. So, just a very fast introduction to DAS, as there's already another webinar already addressed these topics. So basically, with DAS, we exploit an interrogator, a laser interrogator connected to a fiber optic cable, which sends high frequency laser pulses and listen for the best scattered wave field. And basically, the distributed acoustic sensing exploit the capability of providing very high resolution map of the local strain or strain rate. Basically, we map in space and time the local deformation of the fiber optic cable, obtaining this resulting very nice images, which often resemble reflection seismology data, I would say, but in this case, these are a collection of thousands of seismograms in a single image, which record seismic phases between time and space. So focusing on DAS data in those integrated networks, and again giving a bit of introduction to the topic, how do these data, so the surface data from surface-based fiber optic cable and data from in-well fiber optic cables, how do they look like? So first, we start with data from surface cables. This is an example from a fiber optic cable in Greece, connecting the islands of Kefalonia and Ithaca with a sea bottom section of the cable, highlighted in light blue. So basically, so that's the situation. The hybrid network is composed of 7 sparse sensors and the fiber optic cable connecting the islands of Kefalonia and Ithaca. With those data are already available I suggest you to go and read this preprint, and also the fact that we have open source data right now. So please give it a look to this preprint. Basically, this dataset is composed on thousands of earthquakes recorded by DAS from an earthquake sequence northwest of Kefalonia, which we relocated using both the on-land sensors and the DAS cable, showing an improvement in the magnitude of completeness with thousands of additional detections using DAS. And so this is again one of the example of actually two events in 20 seconds recorded by this fiber optic branch between fiber optic cable between Kefalonia and Ithaca. So just to focus a bit on how this surface-based data look like, here we have so on the x-axis the space, on the y-axis the time. We have a collection of 7,000 channels, and what we observe is, especially in the on-land part of the cables, or Kefalonia, or especially in Kefalonia, we observe a strong spatial variability in signal quality, given the fact that the cable is, in this case, running along civic routes, and with cars affecting the recordings, but also the fact that the cable coupling is varying in this section. But you can also see in the marine section strong reverberations coming by the fact that the cable in this case runs. We are still actually in the let's say interpretation phase of this data, but this should be the effect of either very soft sediments or structures bounding the sea between the sea channel between Kefalonia and Ithaca. Okay, though this was an example of a surface DAS data, but also we have very nice images using data from in-well fiber optic cables. This is an example from the Forge dataset, which is a project on enhanced geothermal systems. We can see an overall. I'm sorry about the fact that in this case you have the time axis on the x-axis, while the space on the y-axis. But overall, what we see, it's an overall improving signal quality compared to surface-based data, but also the fact that in this case we lack azimuthal coverage, given the fact that we have a vertical well. So both pros and cons by merging together horizontal cables and vertical in-well data. So our research questions, given the fact that given these observations on actually recorded DAS data, is okay, but how to improve the near real-time processing on such complex surface DAS data, given the fact that we are observing a shift in seismology from the conventional tens, hundreds point sensors to thousands sensors very close together. The second question is how can we efficiently integrate this very dense data into the existing sparse based infrastructures. So we to improve the near real-time processing, other questions arise, for example, how to handle transient noisy traces, or either ensure expert evaluation of few dust traces. And also, more importantly, also how to speed up data transfer. Instead the integration of dust with conventional infrastructures, the problem arises from the fact that we are merging thousands of observations very close together in space with tens, hundreds of observations sparse and on the surface. And so the problem here is how to guarantee a balanced integration, given the fact that we have different numbers of sensors merged together. So what we try to answer those to deal with those issues with a tool for efficient use of dust data, which is an automatic dust channel selection tool, which try to let's say provide few good quality channels along the cable, also taking into account the spatial coverage and not only the waveform attributes. Those data, those selected channels can then be merged with the sparse conventional network. So for this channel selector, we should take care of some ingredients for seismic monitoring. First of all, we must care about the ability to isolate good quality channels, but also to ensure sufficient spatial coverage of the selected channels, given the fact that for source characterization, we need observation coming from different parts of the cable to ensure azimuthal coverage. But this selector should be also independent, robust to different type of deployments, and more importantly, operate in near real time for improving the efficiency of dust data analysis. About the first ingredient, one can easily consider waveform attributes estimated along the cable, which of course are different if we consider the surface based cables or the in-well cable, given the fact that we usually have fewer noise sources in wells, but also the fact that we have different coupling, spatial variability coming from coupling with the ground of the cable in the surface section. And this work has already been done from, for example, from Rodriguez and co-authors this year, trying to assess and to use a data quality score to select channels. And this might work really well for some dust deployments. And basically use this data quality score, merging together several waveform attributes to select dust channels along the cable. And this can be potentially not ideal for source characterization, given the potential lack of spatial distribution of measurements. That's why in this work we try to insert also the presence of selected channels also in a section of the cable with, let's say, not ideal signal quality. At the beginning, we started developing this selector considering the azimuth. So basically dividing the cable in different sections from the azimuth-based informations. But this might, and so adding new selected channels in the defined sections. But problem is that sometimes this is not sufficient, because what about this the presence of very long rectilinear segments, such as for fiber optic in wells, or either fiber optic cable on the surface running along rectilinear routes. That's why we inserted the capability of in the selector of adding subsections within each section of similar azimuth, and then estimate and then select channels also from those subsections. Now, so given the fact that we developed this framework, the questions are how can we do this automatically and being robust for different type of deployments? And also what we want to do is to avoid selecting channels from sharp cable bending. Why this? Because what we want is to mitigate the mixing of different seismic phases coming from the fact that different sections with different orientations are sensitive to different, more or less sensitive to different phases. So with what we explored, so to be both event dependent and robust to different type of deployments, is a modified version of the dbScan algorithm based both on local cable azimuth, but also on spatial contiguity. Why is this? Because first phase of development of ORION, we tried dbScan with local azimuth, but which has a great potential for grouping sections of similar azimuth. But also what we needed was an automatic identification of the cluster of similar azimuth, but let's say spatially isolated. So what we introduced was let's say improved version of dbScan with which we called a contiguity reinforced dbScan. So merging together the information from azimuth with the information with the spatial position of the channels. And in this case, this is a synthetic example where we show that we are able to correctly identify the clusters of different azimuths, but also identify the cable bending as noise. So those as channels not used for subsequent channel selection. So, so the key factor now to make this operate in near real time, given the fact that spatial clustering is done once per cable, is basically the waveform attributes. So the estimation of waveform attributes is the one impacting the computational cost for each event. And so with ORION, we for each spatial cluster, we consider just 3 waveform attributes: signal to noise ratio, local coherence, and the overall noise content of a seismic trace. So for each defined spatial cluster, we compute those waveform attributes. Then we compute quality score, which merge together, help us to select the dust channels spread all over the dust cable, coming from the fact that we use each spatial cluster and we compute waveform attributes from each spatial cluster. This is a test with synthetic data. It's actually just a toy example using Salvos, so a full waveform simulator before and after contaminating with Gaussian noise to test the selector, to both isolate, select good quality channels and also avoid noisy section, but still providing a spatial coverage of the selected traces. So this was, I mean, the introduction of this tool, which is called ORION, which basically, to sum up, it's an automated dust channel selector that accounts both for waveform quality, but also for spatial coverage along the fiber optic cable. So for a given seismic event, and given from the fact that in the first phase, we divide the cable in different sections using both the azimuth information and the spatial contiguity, we estimate waveform channel quality scores for each cluster, and within those clusters we select data considering also for very long cluster to add this additional sections. So the testing phase of ORION was has been done with several dust geometries. We used actually seven setups, one from in Japan, the Azuma volcano dataset, then another one in the Canary, another one in the Canary Islands, one in urban context, the 4C dataset, one in California, an offshore cable in Monterey Bay, one in an enhanced geothermal system for an enhanced geothermal system dataset, Porotomo, and another one with again an offshore cable in Spain, SAFE project, SAFE project. Okay, so how's ORION working with those with this data? So first of all, with the Azuma volcano dataset, this is the results from the spatial clustering. Basically, in the first part of the cable, which spans a very complex public route, we are able to identify all these different sections of different azimuth, but also few unclustered channels at the cable bending. Then longer sections in the when the cable is running at let's say rectilinear, or sections of fiber optic cable section with no abrupt azimuth changes, which for subsequent channel stacking is not a problem, given the fact that the azimuth varies gently. So for an input from the user of 50 selected channels, this is the distribution of the selected traces, which basically spans the entire cable, either if the actual signal to noise ratio, so the quality of the channel is better close to the channels 1400, 1200, and also some nice signals from cars, but what with the ability of still recovering good or let's say less good channels from also from distant sections is good in this case. Then the other example with the fiber optic cable, an oceanic fiber optic cable in the Canary Islands. Here, given the fact that the geometry is not that complex, it's an oceanic cable, so basically we identified just two cable sections. Here, it's important to stress the fact that for this very long section, there are additional subsections which guarantee the spatial coverage of selected traces, which are again shown on the right for an input from the user of 50 selected channels, which in any case are quite spread in a, let's say, a sufficient part of the cable. Another example from an urban environment for the 4C dataset. Here, it's quite nice because with the spatial clustering at the beginning, you can clearly see the urban texture. So those are all the streets where the actual telecommunication fiber optic cable are installed, but they are nicely mapped from the spatial clustering part of the selector. Few unclustered channels are basically at the intersection, so where the cable bends. And again, on the right, for the same 50 selected channels input, you can see the selected channels, which are again spread along the entire length of the cable. Another example for a marine dataset, a marine fiber optic cable in the Monterey Bay area in California. Here the cable is quasi-rectilinear, but still, since the geometry is defined by few known cable locations, again here we have a quite nice result because the spatial clustering, the automatic spatial clustering, identify all these sections from which waveform attributes are computed and from which channels are selected. And again, for the 50 selected channels are shown on the right. Another example from the Porotomo dataset. Here, basically we have a zigzag geometry, and again nicely mapped from the spatial clustering step of the selector. Here we observe the distribution on the right of the selected channels, where actually in this case are let's say present only in the good signal to noise ratio part, because these two sections are affected by very poor signal to noise ratio. So still you have a quite sufficient spatial coverage, but you also avoid to select very poor channels. And for the last example from again an oceanic cable in Spain, on the left you have the spatial clustering, and on the right the selected channels, which are spread for basically half of the cable length, where, because in the second part of the cable either you can see the actual event, or you have very low signal to noise ratio. ORION, so the selector, gives us also the opportunity for a further expert waveform inspection. So given the fact that it takes, for example, for an input from the user of 50 selected channels, one can either decide to analyze those channels and further inspect them, further inspect the traces with the recorded events. So that's another possibility provided by the selector, which is usually a bit, I would say, difficult, given the fact that you have thousands of observations, and you can basically you have the option of either randomly selected channels, or for example using just waveform attributes to select them. So after the testing phase of ORION on several geometries, we also applied for the first time the selector on a real seismic sequence in Kefalonia in Greece again, and to understand if ORION ensures sufficient spatial coverage for source characterization, which for us is source location. So the workflow is from recorded events, isolate few channels and try to assess if those channels are sufficient for source location or not. So again, just to recall the Kefalonia dataset, which I remind you, it's there's a preprint available and also open source data. So the earthquake sequence is happening northwest of Kefalonia Island, recorded by this fiber optic cable, which is 14 kilometer length. So with the spatial clustering in Kefalonia, we identified 27 sections with basically you can clearly see the difference between the on-length section of the cable, so in Kefalonia and Ithaca, which contains far more section, given the fact that the geometry is complex and the fact that the fiber optic cable is actually running along a public route, and instead the marine section of the cable, so more rectilinear, even or gently varying azimuth, where you have just three actually spatial cluster, and so there additional subsections are needed for ensure spatial coverage. So this is important for Kefalonia. So our what we wanted to be sure that the actual selected channels were sufficiently covering the fiber optic cable, and we actually observe this. This is the frequency of selected channels. The colors represent the different sections. Of course, with brown, you have the presence of additional subsections. And for 284 events recorded by DAS cable. And so you observe quite I would say, quite good an overall coverage of selected channels, both on the inland part and on the marine part, which I remind you are provided by very different waveform attributes, given the fact that the on-land section are very noisy compared to the quiet marine sections. So here you can understand the fact of let's say merging together both the information from the signal quality, so from waveform attributes, and from the geometry of the cable. So how do the selected channels look like? So here we compare the selected channels from our selector, so from ORION in red, with the selected channels from a uniform subsampling along the cable. Basically, we selected 70 channels with ORION, and the same 70 channels, given the fact that we have 7,000 channels available with the Kefalonia dataset on the right. So basically at fixed step along the cable, and you can clearly observe, especially in the on-land sections, that the selected channels are have a better quality compared to any uniform selections. Okay, but I mean, what's the effect of selecting at fixed step interval, or using both waveform attribute and geometry based selection, so ORION? And what we did was assessing this influence by trying to relocate the seismic sequence, so all the 284 recorded events with both ORION selected channels and uniform selection. And we nicely, I would say, observed then, comparing the relocations with a very high quality catalog from merging together both DAS and on-land sensors, we observe a quite important decrease in the distance from that catalog, considering ORION selected channels. So basically, with the uniform selection, you obtained a lot of mislocated events, especially when with low magnitude events. While if you use ORION, you end up with the vast majority of events in the let's say correctly located in the seismic sequence position, which is again northwest of Kefalonia. Okay, so ORION, so the selector, can also be integrated with other tools. In our group, Giulio Pascucci developed a spectral subtraction based approach to the noise DAS data, and what we did was basically integrate ORION with the spectral subtraction based approach. So basically, before denoising and after denoising, you clearly see that signal quality improves, and with the selected traces, you can confirm it by the fact that selected trace before and after denoising are have a better quality. You can also see the signal to noise ratio before and after denoising. This is just to stress the fact that ORION can be easily integrated with other tools to again improve the efficiency of DAS data use for seismic monitoring. And this was an example from the Forge dataset. So this was data from an well cable. But this was also for a surface-based DAS data, again for Kefalonia. before denoising and after denoising, and the selected traces before and after denoising, and the corresponding signal to noise ratio on the right, before in blue and after denoising in red. Okay, but again, is this having some influence on, for example, source characterization, the fact that we merge together both the selected traces and also the denoising approach? And we also nicely observe that before and after denoising, source location improves in precision. Just look at this coherence map for the epicentral location, which actually this is a you see these let's say squares, because to improve the efficiency of our locator, we are considering as a neighbor algorithm based search, so to search only in the high coherence section. But nevertheless, the important fact here is that before and after denoising, you observe an improvement in the source location precision. Another nice integration of ORION is with an hybrid network locator, which is called LION. It's another tool we are developing at University of Pisa, and which is a coherence-based source locator, which basically contains three ingredients. So the efficiency, so the capability of managing spatially dense dust data with fine grids, what I just mentioned before, so the decreasing computational costs by by looking at only high coherence section in the coherence matrix, and the ability to separate the contribution. So provide an event location for the conventional network, for the fiber optic sensor, and for the hybrid network, so for the integrated network between conventional and fiber optic sensors. But also to which guarantee also the balancing of the contribution of dust and the seismometers. And this is done integrating ORION into LION. So the balance again is let's say retrieved by merging together the selected channels from the fiber optic cable using ORION with the sparse surface-based sensors. And these are some results again in Kefalonia using the hybrid network locator integrated with ORION. So you see the location with just the stations, with the fiber optic cable alone, and with the integrated network in orange. And you nicely observe a decrease in the overall distance from the high quality catalog I just mentioned before, using, let's say, considering from the stations up to the fiber with ORION selected channels, and up to the integrated network. So to conclude, what I just today is which is ORION. It's a tool which allows us to efficiently use fiber optic data. It provides both good quality traces, but also taking into account the spatial coverage of selected traces, allow more accurate source location, mitigate the bias in the different number of sensors between dust and conventional sensors, and more importantly, can be easily integrated with other tools, such as advanced denoising methods or hybrid network locator. Okay, about ORION, there's a preprint available also for this study, which I suggest you to go to the preprint, and if you are interested and want to learn more about the development phase, testing phase of ORION. And I'm here to listen for questions, suggestions, or whatever.
Thank you, Emanuele.